Over the next few videos, we're going to talk about applications for the derivative. So we now know a variety of ways to calculate derivatives. How can we actually use derivatives? So the next few videos, we're going to talk about what we call optimization. So most real-world situations are subject to limited resources. The term for that is scarcity. We're subject to scarcity in real life. We don't have infinitely many resources to use, so we have to make sure we use our resources wisely. So for this reason, oftentimes one of the goals is to find the optimal way to maximize our outputs in a situation, which can mean a lot of different things, while at the same time minimizing costs. So we want to maximize productivity while minimizing how much it costs us to do so. So derivatives are going to be useful in helping us find this balance, the balance between maximization and minimization of cost. So over this section, the next couple of sections, we're going to focus on maximization, minimization, or more generally what we can refer to as optimization. So first thing we need to talk about is something called a critical value. So functions and their graphs can be classified based on the intervals. Think of intervals as just ranges of values, specifically intervals of x values, where the function is increasing and where the function is decreasing. So what do these two terms mean? Well, if you're looking at a graph, increasing means the graph is rising as we trace the graph from left to right. So as we go from left to right, the graph is sloped upward. So from a more formal standpoint, if a and b are two x values, two values within the domain of our function, where a is less than b, then we can also say that the function values associated with a and b are such that f of a is less than f of b. So let me pull it up so you can see the whole graph. So we have two x values within the domain of our function, a and b. Notice again that a is less than b. And then the associated function values for a and b are also such that f of a is less than f of b. So if you were to think visually about what's going on, to say that a is less than b is just to say that we're looking left to right. If we're saying that f of a is less than f of b, then we're saying we're sloped upward. So if we're sloped both left to right and going upward, think of that as an upward diagonal. It means our graph is rising as we trace the graph from the left hand to the right hand side of the coordinate plane. Well, increasing means rising, so decreasing means that we are falling as we trace the graph from left to right. So again, if we look at two x values such that a is less than b, looking from left to right, then our function is decreasing over a particular interval if our associated function values are oriented in such a way that the first function value is going to be greater than the second function value. So decreasing just means as we look left to right, our graph is going to be sloped downward. So again, for a less than b, which just means we're looking from left to right, the associated function values are such that f of a is greater than f of b, which means we're going downward. So working left to right and downward means we're sloped downward diagonally. Our function is decreasing. So we have to keep in mind, as we look at the graph of a function, there can be intervals where we are increasing, and then there can also be intervals where we are decreasing. So we're not categorizing a graph as a whole, we're categorizing regions, more specifically intervals of the graph. So breaking down the domain of our function, our x values, into intervals over which we are increasing and over which we are decreasing. Well, how do we determine if we don't have a graph where we're increasing and where we're decreasing? This is going to be determined through analysis of the derivative. Okay, so how is this going to work? Well, if our function is increasing on an interval, which again means we're sloped upward from left to right, I want you to think about what the tangent line would look like at each of these points where we say our graph is increasing. If you were to draw a tangent line at each of these locations, what do those two tangent lines have in common? Well, they won't necessarily be the same line. This looks like maybe it's linear, but we can't officially say it's linear. It's really a curve. So they're not going to be the same line. But what we can say is that the slope at each of these two tangent lines would be a positive number. Well, what was the other name for the slope of a tangent line? That was what we called the derivative. The derivative represents the slope of the tangent line at any particular point on the function's graph. So at locations where our graph is increasing and that our function as well is increasing, we notice that the slope of the tangent line would be positive. So if our function is increasing, that means that the derivative, which again, remember that represents the slope of the tangent line, the derivative is greater than 0 on that interval. It's going to be a positive number. So if our derivative is greater than 0 at any particular location, that means that our graph is increasing at that particular location. Well, same kind of idea if our function is decreasing. Imagine taking the slope of the tangent line at both of those locations. Notice that both of those slopes would be negative. So our function is decreasing on an interval when our derivative is less than 0, when the slope of the tangent line is less than 0 on that interval. So if we were to look at this particular graph, notice we have a few things going on. So as we transition from, for instance, x equals -2 to x equals -1, our graph is sloped upward. So we would say that the function is increasing over that interval. And if we assume that we're just continuing in the same fashion forever and ever, then we could say that we are increasing from -infinity to -1. Over that interval of values within the domain, our graph is sloped upward. All of the tangent lines at each of those individual points would have a positive slope, so our function is increasing. Now, notice when we get to -1, the tangent line goes flat. So at that particular location, we would have a horizontal tangent line. Well, what's the slope of a horizontal line? The slope of a horizontal line is 0. So at all of the x values from -infinity up to -1, the slope is positive. Once we get to -1, our tangent line is horizontal and it has a slope of 0. Once we transition past -1, notice we're now decreasing. All of the additional points here from -1 to +1 have a negative slope. So those would be locations where the derivative is negative, our function is decreasing. Now just like at -1, once we transition along the interval from -1 to 1, once we get to 1, we have another location where the tangent line would have a slope of 0. Again, it would be a horizontal line. And then we transition over and now we have positive slopes again. So we're increasing and our derivative would be greater than 0. But what we really want to focus on now are these locations. So we can break our graph up into intervals where we're increasing and then where we're decreasing. But what we want to focus on is the transition. Where do we transition from increasing to decreasing and from decreasing to increasing? These are what we call critical values. The x values, the locations where we have those transitions, represent what we call critical values. So critical values represent the locations where we change from increasing, in other words, sloped upward, the derivative is positive, to decreasing, or vice versa. So where we change from positive tangents, positive slopes for our tangent lines to negative slopes, or from negative slopes to positive slopes. So how do we know where these locations are going to be? How do we know where we're going to transition from a positive slope on our tangent line to a negative slope or vice versa? Well, if we're going to say that the value x is equal to c, so a specific x value, that location is a critical value of our function if, number one, f of c exists. In other words, there's an actual point on the function's graph at that particular value of x, and one of the following criteria is met. So there's a point at that location, f of c exists, and one or the other things is going to happen here. So the derivative, the value of the derivative at that particular value of x is equal to 0. Well, what does that mean? If the derivative at that x value is 0, that means we have a horizontal tangent line. And just like that graph we looked at a second ago, the locations where we had a horizontal tangent line, those were the locations where we transitioned from increasing to decreasing or vice versa. Now, another possibility that would indicate that we have a critical value where we potentially change from increasing to decreasing or from decreasing to increasing is locations where maybe we have a point that exists, but maybe we don't have a tangent line, so maybe our derivative is undefined. Now, the term we used for saying that the derivative is undefined is undifferentiable. Our function is not differentiable at that location. And we talked about several situations where we would have a function that is not differentiable. So for instance, if we have a jump, if there's a discontinuity in our graph, anywhere where there's a discontinuity, our function is not differentiable. Anywhere where we have a vertical tangent line, our function is not differentiable because the slope of that tangent line is undefined. And then also anywhere where we have a corner, a sharp corner, that particular location also represents a location where our derivative is undefined. But those special types of locations can also represent locations where the shape of our graph changes, where we go from sloped upward to sloped downward or vice versa. So increasing, decreasing, horizontal tangent line is the transition between the two, or maybe a location where we don't have a unique tangent line. How does that relate to maximization and minimization, which was the context for all of this discussion? How does this all relate? Well, critical values, again, they'll tell us where we change from either increasing to decreasing or vice versa, but they also represent locations where we possibly, I'm going to underline that, that's important, where we possibly have what we call a relative maximum or minimum value. Relative as in relation to the points around it. So a maximum in relation to the points around it, or a minimum in relation to the points around it. So a relative maximum is a point that is going to be higher than all of its surrounding points within a given interval. A relative minimum is going to be lower than all of the points around it in that particular interval. So if we were to look back at the graph we had on that first page, again, we noticed the critical values, locations where we would have a horizontal tangent line. Those would be locations where the derivative of our function is equal to 0. So at both of those locations, because the slope of our tangent line is 0, that's the same thing as saying that our derivative is 0. Well, notice here at this location, we went from increasing to decreasing. And so if we were to look at an interval around that particular location where we transitioned, notice that's going to be the highest point within an interval around the point. So we would classify this particular point as a relative maximum point on our function. Another way to say this is we have a maximum value of 4/3 at the location x is equal to -1. So our function has a relative maximum value of 4/3, and this is the location where that maximum is going to occur. Now, as we transition from increasing to decreasing, again, we were decreasing and then we transitioned again there at that location where we had another horizontal tangent line. So there at x equals 1. Well, because around this point, this is the lowest value, we go from decreasing down to this point, and then we transition to increasing again. That's going to be the lowest value in relation to the points around it within an interval. So this would be considered a relative minimum. So we would say this function has a relative minimum value of 0. The actual output is 0. and the location for that relative minimum is x equals 1. But the important thing to notice here is that the locations where these relative maximum and minimum values occurred, these were the locations of the critical values. Remember, critical value just means we transition from increasing to decreasing, or maybe from decreasing to increasing. Well, the locations where we transition are also locations where we potentially peak, where we have a maximum in relation to the points around it, or where we hit a valley, where we have a minimum in relation to the points around it. So critical values are going to be very important if we're talking about maximization and minimization. So all of this, if we put all of this together, this idea of critical values, they change from increasing to decreasing around that value, or from decreasing to increasing, and this idea that we can have sort of a peak or a valley at these locations leads us to what we call the first derivative test. So the first derivative test tells us how to determine if a critical point or value represents a maximum, a minimum, or possibly neither. It's possible we have situations where we have a critical value, we have a critical point, but it doesn't actually represent a maximum, which would be a peak, or a minimum, which represents a valley. Now, another thing we need to keep in mind is we did use the term relative maximum and minimum. So relative means in relation to the points around it. It does not necessarily mean that we've reached the highest point on the graph or the lowest point on the graph. We've just reached a peak or a valley in relation to the points that are around it, in relation to an interval that surrounds that particular location. So here is our first derivative test. So it's named smartly. First derivative means we're looking at the first derivative. So we take our function, we take the derivative. From the derivative, we can find our critical values, and we'll talk about that in just a minute. So assume that x equals c, this particular value of x, is a critical value for our function. So we're looking at an interval around c, so values to the left, values to the right of that particular x value, and we're looking at that point's context within the interval we have set around it. So how do we know if that point represents a relative minimum? Well, what we're going to do is we're going to check the sign of the derivative on either side. Remember, anywhere the derivative is negative, it means we're decreasing. Anywhere where the derivative is positive, it means we're increasing. So if the sign of our derivative to the left of our critical value is negative, and the sign of our derivative to the right of this value is positive, that's our indication that we have a relative minimum. Now, why is this? I don't want you to have to memorize a bunch of things. Why is this? Well, think about what this means. If we have a negative derivative, so suppose this is the point we're talking about. If we have a negative derivative to the left of that, that means we're sloped downward, okay? If we have a positive derivative to the right of that location, that means we're sloped upward. So that means this is essentially what's going on with the graph if we look within this interval that's centered around this particular point at x equals c. In this case, based on how the graph would be shaped in relation to this particular point, this would be the lowest point within that interval, so it represents a relative minimum. So negative derivative on the left, and then positive derivative on the right. Well, how do we know that our critical value represents the location of a relative maximum? Well, to the left, we'll have a positive derivative, and to the right, we'll have a negative derivative. So again, what would this look like? Well, suppose this is the point in question, the point associated with our critical value at C. So to the left, we have a positive derivative, which means our graph is sloped upward. To the right, we have a negative derivative, which means our graph is sloped downward. So that means over this interval, the critical value represents the location of the highest point. So positive derivative to the left means we're sloped upward, we're climbing up to this point, and then negative derivative to the right means we're sloped downward, and then we're declining from wherever that point was. Well, again, it's also possible that we have a critical value, but it doesn't actually represent a lowest point on the interval or a highest point. What could it also look like? Well, notice here the signs of our derivatives changed. So we either went from a negative to a positive derivative, or from a positive derivative to a negative derivative. What if we have a critical value, a location where, again, either our derivative has a value of 0 or the derivative is undefined? So that's what's happening at that particular value, at that particular critical value. But what if the signs of the derivative don't actually change on either side of this x value? So in other words, we go from a negative derivative to a negative derivative, or from a positive derivative to a positive derivative. That's an indication that we don't have either a minimum or a maximum. We just have a point where something happens. So suppose this is our point. What would it look like, for instance, to have a positive derivative and then another positive derivative? Well, we could have something like this, but rather than turning around like we did in this situation, if we continue to have a positive derivative, then that's an indication that this point represents neither a minimum nor a maximum. We can think of it kind of like a wiggle. Well, why did this end up as a critical value if nothing special was happening here? That's because if you were to take the tangent line at that location, the tangent line would be horizontal. In other words, f prime of c would be equal to 0. So it would give us a location of a critical value, a possible location for a maximum value or a minimum value. But if we analyze what's happening to the left and to the right, we don't actually have a location where maybe our derivative changes signs and we turn either from increasing to decreasing or from decreasing to increasing. So this is also a possibility. We can have a critical value, and when we analyze what's happening with the derivative, it indicates that we have something like this. So we have a critical value, but it doesn't represent a minimum or a maximum value in relation to what's around it. So there's a lot going on here. We have to think about all the layers of what's going on here. How do we find our max? How do we find our min? Well, again, we're going to use this first derivative test, which tells us, look at the first derivative, analyze what we see from the first derivative around these critical values. But again, how do we find the critical values? Because using this test, using this table, is dependent on knowing where the critical value or critical values are going to be. Well, remember, a critical value occurs either where our derivative is 0 or where our derivative is undefined. So that essentially gives us 2 steps to solving a problem involving maximization and minimization using this test. So number 1, we need to know what x values meet these 2 criteria. So what x values would make the derivative 0? What x values would make the derivative undefined? Those are going to be our critical values. And those are going to be the values that we apply this table to, that we apply the first derivative test to. So once we know where those locations are, then we're going to analyze the signs of our derivative on either side of those values. And keep in mind, if we have multiple critical values, we have to analyze on either side of all of them. We can have a relative minimum and a relative maximum on a graph, and it's just based on what we notice about the derivatives on either side of those individual values. So number 1, we need to find our critical values, and then number 2, we analyze the signs of the derivative on either side of those critical values. If we go from being sloped downward, decreasing, to sloped upward, that means we have a minimum value at that critical value. If we go from being sloped upward to being sloped downward, well, that means we have a maximum. And then if the sign doesn't happen to change, it means we have something going on that's probably a little bit more like this. You can think of the graph as having sort of a wiggle. That's not really a technical term, but you know what I mean by that. So let's do an example. So again, what's the goal? The goal is to find the locations of our maximum values and our minimum values. Okay, so for this function, f of x is equal to 4x cubed minus 9x squared minus 30x plus 25. The first thing we want to do is find all of the critical values. And then we want to use the first derivative test to determine if they represent relative maxima or minima. That's the plural for maximum and minimum. And then we want to sketch the graph of the function using a graphing utility. In other words, using our graphing calculator. Now we're going to use the graphing calculator pretty heavily here just because it's going to be a really great time saver. Now, in order to find critical values, what does that mean? Well, remember, critical values means either the function's derivative is 0 at that location, or the function's derivative is undefined at that location. So that's what we mean by critical values. Critical values occur where the derivative would be 0 or where the derivative is undefined. Well, notice both of these are dependent on finding the derivative. So anytime we want to find critical values where we potentially have a maximum or a minimum, we have to start by finding the derivative. Everything is dependent on finding the derivative. So let's start by finding the derivative of this function. So we can use the sum and difference rules, go term by term. We can use the power rule, we can use the constant rule. So our first term, we take its derivative, we're going to have 12x squared. Second term is negative, okay? And then we bring down our 2, so 18x. And then our last one is going to be 30, so minus 30. And then we take the derivative of that constant and it goes to 0. Well, this is a polynomial function, which means undefined doesn't mean anything here. We don't have any x values at which this function, specifically this derivative, is undefined. But we may have some locations where this function, or its derivative in this case, are equal to 0. So I'm going to take my function, this new function representing the derivative, and I'm going to set it equal to 0. So my goal is to solve for x in this case. Now anytime I have x squared and I have more than one instance of the variable, that's an indication that we're going to have to factor. So first thing I noticed that's going to make my life a little bit easier, notice we could actually divide out some common values in this case. So each of these is divisible by 6, so we could divide out a common 6 from all three terms. So that would give us 2x squared minus 3x minus 5. And if you divide 6 from the other side, well, you still have 0. So that's good. Now, we need to factor this. I'm going to show you a shortcut for factoring that will make your life a lot easier. So keep in mind, if you're used to factoring something like this and you've learned a specific technique, you know how to factor, that's fine. Use your factoring technique. For those of you who are a little rusty on factoring something like this, I want to show you how you would do that. So the technique I use requires taking your coefficient, which in this case is not 1. If it is 1, it's a straightforward problem. If it's not 1, it's not as straightforward. I'm going to take the coefficient out front and I'm going to multiply it by the constant at the end. So essentially I'm going to move it. And I'm going to star this because I need to remember that I've done this. I've changed something and I'm going to have to change it back at the very end. So I'm going to multiply by 2, move it over here, which is now going to make the coefficient in front of the x squared a 1. So 2 times negative 5 is going to be negative 10. Okay, so now we're working with a different problem, but it's a variation of the problem we started with. Now, why do I do this? I do this because now I have a new form of my problem that's going to be easier to factor. All I have to do now is look for numbers that multiply to give negative 10, that would also add to give negative 3. So if I can find a pair, that pair represents how I would factor negative 10, and then I can write binomials that factor the polynomial based on the numbers I find. So numbers that multiply to give negative 10, but add to give negative 3. Well, that is going to be negative 5, and then positive 2. So how do I know what they're going to be? Well, if they multiply to give a negative, that means they've got to be opposite signs. So I know one has to be positive, one has to be negative. If they also add up to give a negative number, that means the bigger one is going to have to be negative in order to make the output from addition negative as well. And so this is going to be the only pair that factors in this way to give me this polynomial. And of course, we can always FOIL it back out and check, and as long as we get the polynomial we started with, then that indicates that our factorization is correct. Now, keep in mind, if you redistribute this, if you FOIL this, you get back to this quadratic trinomial, not the actual one we were factoring at the beginning. Well, why is that? Well, remember, we changed this polynomial into a simpler form in order to simplify our factoring. But we have to undo the change we made in order to put our problem back where it needs to be. So what did I do to make this change? Well, I took the coefficient in front of x squared and I multiplied it by the constant. So now I have to undo that. In order to undo a multiplication, I divide. So I'm going to take my two constant terms, the ones that represented -5 and now -10, and I have to undo the multiplication by 2, which means I have to divide by 2. So both of the constant terms in my factorization, I then have to divide by whatever I use to multiply by. Now you'll notice one of these divisions, one of these fractions reduces and one does not. Okay, so for the one that doesn't, I'm actually going to bring my coefficient out front and make it a coefficient for the x. So bring the denominator out front, make it a coefficient on x. For the one that does reduce, I do want to reduce it. So we end up with a factorization of 2x minus 5 and then x plus 1. And we can verify that this factorization is correct by FOILing it out and making sure we get back to where we started. So 2x times x is going to be 2x squared. We have a positive 2x minus 5x, so negative 3x. And then negative 5 times positive 1 is going to be negative 5. So this is the correct factorization of our polynomial. And keep in mind, if you factored it in this form, you would just end up with one or more of your binomials having an additional greatest common factor that could factor out. So when you start with a slightly more complicated trinomial, if you have a common factor you can divide out from all three terms, it's a good idea to start by dividing it out so that the problem simplifies a little bit. Well, how does this help us? Well, now we have two numbers that are multiplied together and the multiplication results in a 0, which means that one or the other had to be 0. So I can take each of these factors, I can set each of them equal to 0, and then I can solve for x. So for the first one, I'm going to add 5, divide by 2. So x is going to be 5 halves, and I'm just going to leave it in that form. And for the next one, I just subtract 1, so x is negative 1. So these are going to be our two critical values. These are the two values of x that if we subbed into the derivative would make the derivative 0. So you might take a moment to check it. Double check. If you subbed this into the derivative, your output upon that substitution should be 0, which is the indication, again, that these two are critical values. So what does that mean? What that means is that these are the two locations within our domain where we could possibly change from increasing to decreasing or from decreasing to increasing, which also means that those are the potential locations where we could have a relative maximum or a relative minimum, where we could have a peak on our graph, where we could have a valley on our graph. So how do we know what's happening on either side of these? Well, we're going to use what we call a sign chart. This is just going to help us organize our information based on these critical values and then the intervals around them. So I'm going to think of this like the x-axis, and I'm going to put my two x values on there. Now make sure they go in order. Spacing doesn't matter, but they do need to go in the correct order. So negative 1 is the leftmost value, and then 5 halves is the value on the right. I'm going to box these in because I'm about to add a bunch of numbers to this number line, and I want to make sure I know what's a critical value and what's not a critical value. Okay, so what we want to know now is what's happening to the derivative on either side of these values. So specifically, for anything that's less than -1, for something that's between -1 and 5/2, and then for something that's greater than 5/2. What is the sign of the derivative on those intervals? So I'm going to pick what we call a test value. Within each of those intervals, I just want to pick some value of x, and I'm going to determine what happens for that value of x. If these are the only critical values, that means these are the only locations where we can possibly change signs in our derivative, where we can go from increasing to decreasing or from decreasing to increasing. So whatever happens for one value within each of these intervals essentially represents what happens for every value within each of those intervals. So we pick a test value that sort of represents the interval and what's going to happen for all of the values on that interval. Now, it doesn't matter what you pick, but you don't want to pick something that's going to be difficult to plug into a function. So ideally, pick small numbers, pick whole numbers whenever possible. So something less than -1, how about -2? That's an easy one. Something between -1 and 5/2, well, we've got options, but notice that 0 will also be between those, and 0 is pretty much always easy to substitute into a function. And then something that's greater than 5/2. Well, what is 5/2? Let's make sure we know what that is as a decimal. So that's going to be 2.5. So something bigger than 2.5, maybe 3. And again, keep in mind, you can pick any number you want in these intervals. We're just going to pick values that will probably be easy to sub into our derivative in order to determine the derivative sign. Okay, so what we want to do now is determine what would the sign be for the derivative at each of these values of x. So specifically, f prime of -2, what's that? F prime of 0, what's that? F prime of 3, what's that? We want to know what the derivative is at each of these locations, but more importantly, what is the sign of the derivative at each of these locations? Is it a positive derivative? Is it a negative derivative? So what are we actually doing? Well, literally, we're taking each of these values and we're substituting it into the derivative, checking the output sign. We can save a little bit of time by taking our graphing calculator and just typing in that derivative. So I'm going to type in the expression for the derivative. So 12x squared minus 18x minus 30. Okay, I don't want to look at the graph yet. I just want to look at the table. So I'm going to go into second and graph and go into the table. How is that going to help me? Well, this gives me all the different x values, specifically increasing by increments of 1 each time. So I can scroll through the table, I can find the associated y value for any integer x value. But I want to check specifically what happens for -2, for 0, and for 3. So rather than having to take a moment and actually plug these into the function, by using my table, I can find these and not really have to do any extra work. So f prime of -2. Okay, so there's x equals -2. Notice the associated y value is 54. Okay. Now what about 0? So if we go to 0, f prime of 0 is -30. And then f prime of 3, positive 3, is going to be 24. Okay, so I'm not worried about how big the number is, how small the number is. All I'm worried about is, do we get a positive output or do we get a negative output? Well, for a test value of -2, we get a positive output. For a test value of 0, we get a negative output. And then for a test value of 3, we get another positive output. So what does this mean in terms of how the graph would be shaped? From a standpoint of the function increasing and decreasing, what does this mean? Well, anywhere where the slope is positive, our function is increasing. So I'm just going to draw roughly what increasing looks like. It just means we're sloped upward from left to right. Anywhere our function has a negative derivative, the function is going to be decreasing. So it's sloped downward as we go from left to right. And then again, we have another positive derivative, so that means the graph is increasing again. So we'll classify what's going on in just a minute, but sometimes we just want to know where is the function increasing, where is the function decreasing. Specifically, what intervals are we increasing over, what intervals are we decreasing over. Well, notice we have two intervals along our domain, along the x-axis, where our graph would be increasing. So all the way from negative infinity to negative 1, and then all the way from 5/2 to positive infinity. Over those intervals, our function is increasing. So we can say our function is increasing on the intervals from negative infinity to negative 1. Now I use parentheses with negative infinity because negative infinity is not a number. I'm also going to use parentheses at negative 1 because once we get to negative 1, that's a critical value. We don't actually have a positive derivative there. What do we have? At negative 1, the derivative is 0, which means we're no longer increasing. It means we've hit a flat line. Okay, so over that interval, up to negative 1, but not quite reaching negative 1. Now also, we're increasing on the interval from 5/2 to infinity. So union, which means we're going to join these two intervals together, union 5/2 to infinity. And again, I'm going to use parentheses with infinity because infinity is not a number that we can reach. And I'm also going to use parentheses with 5/2 because at 5/2 the derivative is 0. It's not a positive derivative, it's a 0 derivative, which means we would stop right before we get to 5/2 in terms of classifying our function as being an increasing function on this interval. Okay, now the interval from negative 1 to 5/2, notice that's where we would be sloped downward. So we're decreasing on the interval from negative 1 to 5/2. And notice again I'm using parentheses because at those two locations the derivative is not negative, the derivative is exactly equal to 0. So that classifies in general what we're seeing with our function in terms of what the shape of the graph would be. It's going to be sloped upward, and then sloped downward, and then sloped upward again, and it changes at those two locations, those two critical values. Well, we really wanted to focus though on the maximum values, the minimum values. So how do we know we have a maximum? How do we know we have a minimum? Well, we can go back to the chart on the previous page, but let's just think more what the graph would look like. If this were happening, we're going upward and then suddenly we turn and we go downward, which means the location where we change from increasing to decreasing, that's going to be the highest point. We're reaching a high point and then we're decreasing from there. So this is going to be the location for a relative maximum. Now if we go from decreasing and then we begin increasing again, the point where we change over represents the lowest point. It represents a minimum. It's the lowest point, and then we begin increasing again from there. So these two critical values, x equals negative 1 and x equals 5/2, represent the locations of our relative maximum and minimum values. Negative 1 is the location for our maximum, and then 5/2 is the location for our minimum. So we have a relative maximum. Well, what's the value? We'll determine that in a minute. We have a relative maximum occurring at x equals negative 1. And we have a relative minimum occurring at x equals 5/2. And again, we see that based on the behavior of the derivative around those two locations. Well, what we really want to know though is what is the maximum value? What is the minimum value? What's the highest value we reach? What's the lowest value we reach? Okay? So before we do that though, I want to look at the graph of the derivative. Before we clear out the derivative, throw it away, graph something else because we want to graph the actual function, I want to look at the graph of the derivative as well and show you how you can use that. So notice we picked our test values, we determined what behavior we would see in terms of increasing and decreasing based on those test values and based on what we saw in the table with the derivative. But what would we see from the graph of the derivative? So let's look at the graph. Okay, So I'm going to zoom out. And notice I'm still centered there on that location. Okay. Now what am I seeing? Well, what I'm noticing, number one, where's the derivative 0? Let me go back into the table real quick. Notice where the derivative has a value of 0. We have a value at -1, and then we don't see the other value, but right there between 2 and 3, that's where we go from a negative derivative to a positive derivative, which means we've crossed over somewhere there. We know that location where we cross over happens to be at 5/2. But what are we seeing from the graph? How can you determine what you need to know from the graph? So now we can see in general what it looks like. I'm going to zoom back in. I'm going to go to Zoom Standard. Okay. What I want to focus on are those two locations where we cross over the x-axis. Specifically, what is happening on either side of those locations. Well, there at x equals -1, that was one of our critical values. Notice to the left, we're above the x-axis, and to the right, we're below the x-axis. Well, think about what this graph represents. This graph represents the derivative. So to the left of our critical value, our derivative is positive, hence the positive sign, and hence the fact that we're increasing. Now, notice the graph here is not increasing, it's decreasing. But we're focused on the signs we get from this graph. This is not the graph of the original function. This is the graph of its derivative. So for any of the values that are less than -1, less than x equals -1, the derivative, its value is represented above the x-axis, so the derivative's value is positive, which means the actual function's graph, which we don't have graphed, would be sloped upward. Now, as we go from -1 below, so -1 over to the next critical value, which was at 2.5, 5/2, notice over that interval, the graph is going to be below the x-axis, which means all of those y values are negative. Well, again, those values represent the value of the derivative at those particular locations. So from -1 to 5/2, we're below the x-axis, which means our derivative has a negative value. Well, anywhere our derivative has a negative value, that means the graph of the actual function would be sloped downward. And then as we go from 5/2, where we cross back over, to infinity, notice the values there are going to be positive. We're now above the x-axis, so our derivative has a positive value. So we can determine that from the table, from taking some actual values, some test points, but just looking at the graph, we can also see over this particular range, we have a positive derivative, which means we're sloped upward, the actual graph is. We have a negative derivative, which means we're sloped downward, and then sloped upward again. Okay, so that's just kind of a time saver, and it's important to be able to interpret what we're seeing from the graph of a function and from the graph of its derivative. So now we need to answer the question, now that we know where the relative maximum and where the relative minimum occur, these are not the actual maximum and minimum values, they represent the locations for them. The maximum and minimum values represent the values that the function will take on, the actual y values associated with those particular values of x. So for x equals -1, we know that's the location of our relative maximum based on what we saw with the derivatives. We want to know what is the actual maximum value. In other words, if we were to plug that x value into our original function, well, what would be the output that we would get? So we're evaluating f of -1, which means we're taking this input and we're plugging it into our function. So 4 times -1 cubed minus 9 times -1 squared minus 30 times -1 plus 25. So I'm going to show you a couple different ways you can evaluate this. One way you can evaluate this is using the graphing utility, but keep in mind what we have graphed right now. We have the derivative graphed. If we want to get the function values, we need to graph the actual function itself, which we wanted to do anyway. We wanted to sketch using a graphing utility at the very end. So let's go ahead and do that, and then we can use this graph. So we have 4x cubed minus 9x squared minus 30x plus 25. Okay, now right now we're just focused on values. So let's just look at the table and let's see if we can get the values we want. So second in graph is going to take me into the table. I want f of -1. Well, f of -1 is going to be 42. So that's going to be 42. Now, what happens if we evaluate at x equals 5/2? Remember, that means we're plugging 5/2 into our original function. Okay. Notice we don't see 5/2 here on the table. That's because we're increasing by intervals of 1. Okay. So we can change a table setting and we can find this value if we want this value. So I'm going to go second in window into the table settings. And you can either change how your x values increase, or if you just change from independent auto to ask, which we've done before, and then go back into the table, notice it's blank because it's going to let you type in the x values you want. So I want to evaluate with an x value of 5/2. Okay, and I get -43.75. Well, that's going to be the value, but the problem is it's in a decimal form. Ideally, we want to have it in a fractional form. So if a decimal form is okay, well, then we're good. If we want the fractional form, the table may not be a great option for us. So what do we do if we want the fractional form rather than the decimal form? Well, that's when we're going to have to actually use the function itself and evaluate it algebraically. So evaluation here means I'm plugging into my function, specifically substituting this value of x equals 5/2. Well, we can determine this again from the table, which we just did, but if we want to go real old school, just plug it in, right? So just substitute all of this in, type it in. So we have 4 times 5/2, and that is cubed. Okay, be careful, make sure you have all those parentheses where they need to be, minus 9 times 5/2 squared, minus 30 times 5/2, okay, plus 25. And there we go, and that's what we're evaluating. So double check you typed everything you wanted, and then just hit enter and it evaluates. Well, notice it gives you the same value here. Well, did it really do anything? If it just gave us the same value, how does that help us? Well, once it's on the actual home row and we can just evaluate things the way we just did, we have another option for how to look at our answers. So normally our answers are given as decimals like we have here. If you go to the math menu though, option 1, arrow frac, will take that decimal and if possible, it will convert it to a fraction. And so there we go. That's going to be the actual value we want. And unfortunately, the table is not going to give you that improper fractional value. So in this case, actually typing in and evaluating the function that way is really going to be the only way to go to get that fractional value. So what does this tell us? Well, it tells us x equals -1, which was the location of our relative maximum, is associated with a maximum value of 42. That means that's the actual relative maximum. That's the actual function value. That's the highest function value in relation to the x values and their associated function values around x equals -1. And then our relative minimum value, the lowest value in relation to everything else around it, is -175 over 4, which we know is the same thing as -43.75. And then last but not least, let's look at the actual graph and see what we can interpret. Now, notice here, it looks like we've got some breaks in the graph. We really don't. It's just because we're zoomed in such a way that we can't see everything. So if we were to zoom out, we may be able to see a little bit more. There we go. We can kind of see the peak and the valley. So notice we go from increasing, and then we peak there at x equals -1. Again, it's a little harder to see. We'll zoom back in a minute. We drop back down, so we go from increasing to decreasing, and then we hit a valley, which happens to be at x equals 5/2, and then we're increasing again. So our increasing and decreasing intervals make sense. Let's go back to Zoom Standard. And again, we can see where specific things are happening. So we peak at a certain point, we decrease, and then we go back up again. And so that gives us the locations for increasing and decreasing, and that peak and that valley represent our maximum and our minimum. So again, notice a lot of layers involved in doing a problem like this. So before we try another example, I just want to recap all of the steps we took. What did we actually do here? Well, we started by finding the critical values. The goal is to find relative maximum and minimum values. In other words, highest or lowest values in relation to the other values around those particular x values. So those are always going to occur wherever we have critical values. Not every critical value represents an extreme, a maximum or a minimum, but those will be the only locations where one of these values could occur. So we start by finding the critical values. Well, from a practical standpoint, that means take the derivative, and we want to know where is the derivative equal to 0 and where is the derivative undefined. Those are going to be the two criteria that would give us critical values. So based on the structure of our derivative, there aren't going to be any values where it's undefined, but we did determine where it would be equal to 0. So we factored that, found the associated x values. Okay, so those are going to be the possible locations of a maximum or minimum. So in order to organize our information, we drew a sign chart, which just allows us to analyze what's happening on either side of those critical values. So we determined both algebraically and graphically that everything less than -1 will have a positive derivative. Everything from -1 to 5/2 will have a negative derivative. And then everything from 5/2 to infinity will have another positive derivative, which tells us we go from increasing to decreasing to increasing, which allows us one way to classify our function and classify its graph. Now, based on how we change in terms of our behavior, that tells us where we hit a maximum and where we hit a minimum. So we go from increasing to decreasing, which means we hit a maximum, and then we go from decreasing to increasing, which means we hit a minimum. So the critical values are not the actual maximum and minimum values. They represent the locations for the maximum and minimum values. So by plugging in these values to our actual function, we find the maximum, the highest value, the relative maximum, and then the relative minimum, the lowest relative value, in relation to all of the points around that location. Okay, so let's try another example. Again, same kind of layers, same kind of structure. What changes is the function we're looking at. Okay, so for f of x is equal to 2x cubed minus x to the 4th power. Again, we want to find the relative extrema. Okay, so it's phrased a little differently. Relative extrema is a more general term for maximum and minimum values. So extrema, that's the general term for both maximum and minimum values. It's the extreme values, okay? And then again, we want to sketch the graph using a graphing utility. So what do we need to do? Well, relative extrema, relative maximum and minimum values, those occur where we change from increasing to decreasing or from decreasing to increasing. And those locations occur wherever we have a critical value. So we need to start by finding our critical values, which means start with the derivative. Find the derivative of the function. Okay, so let's differentiate this. F of x is equal to 2x cubed minus x to the 4th power. So we can use the power rule, we can use the difference rule. So our derivative is going to be 6x squared minus 4x cubed. Okay, so again, we have a polynomial derivative. We don't have any x values where this will be undefined, but we may have some x values where this is equal to 0. So we're going to start by taking this, setting it equal to 0. What values make this 0? Now, here's something that's really tempting to do that you can't do. You cannot move this term over and then divide out x squared on both sides. That would allow you to isolate x, but anytime you divide out and eliminate instances of the variable, you lose possible solutions to your equation. So anytime you have more than one instance of the variable and you have higher exponents, something squared, something cubed, anything higher than just a first power, that is an indication that you have to factor, just like we did with the last problem. Well, here we can divide something out again to start with if we'd like. So notice our coefficients, not our x's, but our coefficients have a common factor of 2. So we can divide out that 2 if we want. So if we divide 2 from both sides, that's going to give us 3x squared minus 2x cubed, and 0 divided by 2 is still just going to be 0. Okay, well now nothing is in common except for our x's, but the x's represent the greatest common factor. So we have 2 x's in the first term, 3 x's in the second, so we have 2 x's in common. So I'm going to factor out that common x squared. Well, what is that going to leave me with? Well, my first term, we factored out the x squared, which means we're left with 3, and then the x squared is gone. Okay, and then for the second term, minus 2, and we had 3 x's, factored out 2 of them, which means there's only one of them left, so 2x. Okay, now that we have our 2 factors, again, 2 factors, we take their product, and the product is 0, which means one or the other has to be 0. So we can take each of these, set each of them equal to 0, and then solve for x, solve for our critical values, those 2 values that would make our derivative equal to 0. So if x squared is equal to 0, we could take the square root of both sides, and we know x has to be 0. In this case, we could add the 2x and then divide 2, which means x is going to be 3/2. So 0 and 3/2 are our critical values. So in order to determine what's happening on either side of those critical values, whether either of these represents a maximum or a minimum, we do our sign chart. So here's 0, here's 3/2. Make sure you write them in order. And again, I'm going to box each of these in. Okay. Now we want to determine what's happening on either side of these values. So this time, let's see if we can maybe use the graph. Okay, so I'm going to graph the derivative like I did before. Let's graph this derivative. So 6x squared minus 4x cubed. Okay, there's our derivative. Double check that. That looks good. I'm going to graph this. Okay, so what can we see from this graph? Now, again, be careful. This is not the graph of the original function. This is the graph of its derivative. So let's zoom in just a little bit. And I'm going to keep myself centered at the origin, but I'm going to zoom in a little bit. Okay, and I can see everything I need right here. Well, what's happening at these specific locations? Specifically, what do 0 and 3/2 represent? They represent the locations where the derivative is equal to 0. So if we look at the 2 x-intercepts on this graph of the derivative, the first x-intercept occurs at 0, and the second x-intercept occurs at 3/2. Okay, what can we also determine from this graph? What we really want from this graph is related to the signs of the derivative, specifically the signs on either side of these specific critical values. So what can we say about x values that are less than 0? Specifically, what can we say about their derivatives? Well, for anything that's less than 0, the derivative at that location, everything less than 0, looking at the graph of the derivative, notice all of the y values, all of the outputs for anything less than 0, those are going to be positive. So the derivative for any x value that's less than 0 is going to be greater than 0, because all of our x values less than 0 are corresponding to y values above the x-axis, so all of the derivative values are greater than 0. Now again, don't forget, this is not the graph of the function, this is the graph of the derivative. So when we're looking at each of these points represents the value of the derivative for our function. So for any x value less than 0, the derivative has a positive value. Now, once we get 2x equals 0, that's where we have a horizontal tangent line. The value of the tangent there, or or the value of the slope of the tangent is going to be 0 because the derivative is 0 at that location. Now, what can we say about values that are then greater than x equals 0? So once we get past x equals 0, what's the sign going to be for the derivative? Well, notice we hit the x-axis, but then we turn around and go back in the direction we came from, and the outputs are again positive. So between 0 and then our next critical value at 3/2, we're still above the x-axis, which means the derivative is still going to be a positive number. What happens when we get to 3/2? Well, once we get to 3/2, we go from having a positive derivative to having a negative derivative. We drop below the x-axis. So along that interval, our derivative is going to be less than 0. It's going to be negative. So what does this mean from the standpoint of increasing and decreasing? And I'm going to get out of this graph because I don't want the graph to confuse us. We just need to think about the derivatives here. So anywhere where the derivative is greater than 0, remember that means our function is increasing. So if we were to look at the actual graph of the function, because the derivative at each of these locations is greater than 0, the graph of the function is going to be increasing. Now once we get to 0, again, that was a critical value. That was a location where the derivative had a value of 0. But what can we say about values between the two critical points? Well, again, the derivative was still positive, which means we're still increasing. We have a critical value, but to the left of it and to the right of it, the function is continuing to increase. Now, once we get to 3/2, suddenly our derivative is negative once we cross over that. So we go from increasing to the left of 3/2 to decreasing to the right of 3/2. So this will tell us where we're increasing and where we're decreasing. So let's focus on those intervals first, and then we'll talk about maximum and minimum values. Okay. Now, it may be tempting to say that we are increasing all the way from -infinity to 3/2 because we're increasing over both of those intervals. That's not quite correct, though. We're increasing from -infinity to 0, but remember at 0, that's where we had a derivative of 0. That's where we had a horizontal tangent line. So that's a little gap in these two intervals. At this location, we are not increasing. We're increasing over values to the left, and we're also increasing over values to the right. So we have two separate intervals where we're increasing. We can't join them together and say we're increasing over this whole interval. We have two separate intervals broken up around that critical value. So we're increasing on the intervals from -infinity to 0, again, not including 0. And then we're also increasing on the interval from 0 to 3/2. And then once we get to 3/2, our derivative had a negative sign, so we're decreasing. So we're decreasing from 3/2 all the way out to positive infinity. Now, based on what we're seeing here, what can we say about maximum and minimum values? Okay, well, to the left of 0, we're increasing. We get to 0, and we know we have a horizontal tangent line there. Okay, but what happens to the right of 0? Well, we go from increasing to a horizontal tangent line to increasing again, which means at this location, we may have that horizontal tangent, we may have a critical value, but we don't have a maximum or a minimum. We go from increasing to flat to increasing again. So this is a critical value that represents neither a maximum nor a minimum. It's just a critical value. It's just a location where we have a horizontal tangent line. Now, 3/2 on the other hand, we go from increasing to decreasing on the other side. So that means we have a peak in the middle. So this is going to be the location of a relative maximum. Well, these are our only critical values. So we don't actually have a relative minimum in this case. We don't have a valley represented on this graph. The only special location we have represents a relative maximum. So our relative maximum occurs at x equals 3/2 And we don't have a relative minimum, so not applicable. That doesn't apply here. We just don't have one. And again, this location categorized as neither. Nothing special happens there. But we do want to know what that value for the relative maximum is. So in other words, what is the function value at x equals 3/2? That's the question. Okay, well, let's plug that into the function again. So that's going to be, or let's see, I think I was underlining the derivative, the actual function. Remember, we want an output for the actual function, the actual y value at that location, not the value of the derivative, but the actual y value. So that's going to be 2 times 3/2 cubed minus 3/2 to the 4th power. And as we saw with the last example, plugging in and trying to get an output for a fractional input may lead us to a decimal in our table. So let's just plug this one in. Let's just do this one, just evaluating by typing in. So 2 times 3/2, and it's raised to the 3rd power, minus 3/2, and it's raised to the 4th power. Okay? And then we hit enter, and there we go. Now again, remember, we don't want the decimal, we want the fractional version of that. So I'm going to go to the math menu, arrow frac, and convert it to a fraction, and that's going to be 27/16. So that is going to be the relative maximum value. In other words, that's the highest value our function hits in relation to the points around that. So that represents the location where we peak on our graph. Okay, and then last but not least, let's look at the actual graph of this function. So what do I have typed here? I have the derivative typed. That's what we use to analyze our sign chart. So let's clear that out, and then let's type in our actual function. So 2x cubed minus x to the 4th power. Let's see if we can spot some of those special sort of things. Okay, well, if we were to zoom standard, just to get a bigger picture, notice all of the special stuff going on we can see when we're zoomed in. Okay, so we go from increasing, and then let's zoom back in. Enter, zoom, there we go. Okay, so the locations where we have a horizontal tangent line, we have one right there where my cursor is at x equals 0, and then we also have a horizontal tangent line to the right of that. Where does that occur? Well, remember, that's going to occur at 3/2. Okay, so there at 0, we see why we don't have a maximum and don't have a minimum. If we look at the slope of the graph to the left of that location, it's sloped upward. We get to that point and we have a horizontal tangent, but once we cross over that point, we're still sloped upward. So we have the critical value because we have a horizontal tangent right there, but we go from increasing to increasing again. So we don't actually have a relative maximum or minimum there, we just have a little wiggle in the graph. Now once we get to x equals 3/2, to the left of that location we're increasing, and to the right of that location we are decreasing, which again we noticed from the derivative. So that's going to be the location for a relative maximum. Okay, let's look at one additional example, and then we'll talk a little bit about graphing. How can we graph a little bit more accurately using this idea of the derivative and this first derivative test. Okay, so for f of x is equal to x minus 2 quantity raised to the 2/3 power plus 1. Again, we want to find the relative extrema and then sketch the graph using our graphing utility. Okay, so we need to find the critical values in order to find the possible locations for those maximum and minimum values. We check the derivative on either side of those locations, and we interpret what we're seeing based on the values for the derivative. Okay, so let's start with our derivative. Now we're going to need the chain rule here. So remember, differentiate the outer function. Here we can essentially use the power rule, so bring down your 2/3 and then decrease it. And then we just have x minus 2 inside, and then we multiply by the derivative of the inside. So bring down the 2/3. Okay, so 2/3, new exponent is 2/3 minus 1, which is going to be negative 1/3. So 2/3 times x minus 2 raised to the negative 1/3. And then we multiply by the derivative of the inside function, which will just be 1. And then if we differentiate the plus 1, it just goes to 0. Okay, so let's write this in a little bit better form. Ideally, we don't really want to have fractional exponents if we can avoid it, and we definitely don't want to have negative exponents. Okay, so what are we really looking at here? Well, multiply by 1 doesn't mean anything. What does the negative exponent mean? It means we take it to the denominator. It means we take the reciprocal. So 2 is going to be in the numerator. We already have a denominator of 3, and the negative exponent tells us we can put this down in the denominator with 3. And if we want, we can just leave it as a 1/3. I do want to show you both ways though. So we can leave it as a 1/3, but what does an exponent of 1/3 mean? It really means we have a cube root. So we really have 3 times the cube root of x minus 2. But ultimately, we're not focused here on simplifying the derivative. We're just focused on finding the derivative and then using it. Okay, so we have our derivative. Now we need to find our critical values. So what are our critical values going to be here? Well, remember, they'll either occur where our function is equal to 0 or where our function, specifically its derivative in this case, is undefined. Okay, so where is this function, specifically the derivative of our original function, where is it equal to 0 and where is it undefined? Well, if you think about the structure of this function, could it be equal to 0? Could we possibly have a situation where it's equal to 0? Well, the only way we can divide two numbers and get an output of 0 is if the numerator is 0. So it would have to be 0 over something else. Okay, so 0 divided by anything except 0 divided by 0 gives us an output of 0. Well, here's a problem though. Notice our numerator is just 2. It's identically 2, and we don't actually have a variable in the numerator. So if the numerator is always 2, there's no way to get a numerator of 0. So that means this particular function, representing our derivative, cannot be equal to 0. There won't be any x values that make this equal to 0. But remember, that's not the only definition of a critical value. A critical value can also occur where the function is undefined. Well, notice here we have a function with a numerator and a denominator. If the denominator were 0, that would mean the function is undefined. So we may have a critical value because the function could have a denominator of 0, which again means the whole thing is undefined. So even though the whole thing can't be equal to 0, if the denominator is equal to 0, well, that also means that we found a critical value. So let's take the denominator and set it equal to 0. And you can use either form, doesn't matter. Let's use the one with the fractional exponent. So 3 times x minus 2 to the 1/3 power is equal to 0. Now, don't be alarmed. This looks like it would be a complicated thing to solve. It's not going to be as bad as you think. So we need to work our way outward in. So first thing we'd have to do is divide out the 3 on both sides. So that's going to leave us with x minus 2 to the 1/3 power is equal to 0. Well, if we take a number and raise it to a power and get out 0, that means the number that we raised to the power had to be 0. The only way we can get a 0 as an output from exponentiation is if the number we raised to the power is 0. So that means that x minus 2, the number in parentheses, also has to be 0, which gives us a critical value of x equals 2. So if x equals 2, the derivative is not 0, but the derivative is undefined. If we were to plug in a 2 here or plug in a 2 here, we end up with a denominator of 0, which means the derivative is undefined, which represents a location for a critical value. Now, notice here we only have one critical value, so we only have to analyze 2 intervals on this graph. So our critical value occurs at x equals 2. And then the question is, what's happening to the left of that? What's happening to the right of that? Okay, so let's plug in our derivative to the graphing utility, and we'll use the graph to determine what we can see. So how you plug this in is really up to you. I would potentially use the fractional exponential version here. Be careful when you type this in though. So when you type this in, 2 divided by, make sure you put parentheses around the whole denominator. So divided by 3 times x minus 2. Now x minus 2 is raised to the 1/3 power. Now notice here the 1/3 is only going to apply to the x minus 2. It's not going to apply to the 3. So there we go. So once we have all of those parentheses, double check that you close every set of parentheses. That is going to be the function representing our derivative. So let's go look at the table for that. Okay, now I still have the independent ask setting on, so let's set it back to auto. And then let's go back into the table. And there we go. Okay, so where was our critical value? It was at 2. Notice what happens at 2. We have an error. Well, that makes sense, right? If the graph that we just graphed, if the function we just graphed represents the derivative, and we said this is the location where the derivative is undefined, well, it makes sense that we get an error. It means the derivative doesn't exist there. But what we're interested in at the moment is what's happening to the left of that, what's happening to the right of that. So to the left of x equals 2, our derivative, notice all those values are negative, so the derivative is going to be less than 0. What about to the right? Well, if we look at x values that would be greater than 2, all of those values are positive, so the derivative has a value that's greater than 0. What does this look like on the actual graph? Well, there's our graph. Notice we have an asymptote, so we have an asymptote there at x equals 2. To the left of x equals 2, all of the values are below the x-axis, which means the derivative has a negative value, since again, all of those values are representing derivative values. And then to the right of 2, to the right of that asymptote, the graph is going to be above the x-axis, so the derivative values are all going to be positive. So from the standpoint of the actual graph, the actual function, again, let me get out of there so we're not confused by that. If our derivative is less than 0, it means we're decreasing. And then if our derivative is greater than 0, it means we're increasing. So we are increasing on the interval from 2 to infinity, not including 2, because again, 2 in this case, 2 doesn't even exist. 2 doesn't even represent a point on the graph. Well, actually it does. So 2 here, 2 is where the derivative is undefined, excuse me. So 2 minus 2 would be 0, 0 to the 2/3, and then plus 1. So it is a point, but notice again, that was the location where the derivative was undefined because we had that asymptote on the graph of the derivative. But at this location, we are neither increasing nor decreasing, so we have to be careful writing our intervals. And then we're decreasing on the interval from negative infinity to 2. Well, based on the fact that we do change over, what can we say about the location for that critical value? What does it represent? Well, we go from decreasing to increasing, which means this is going to be a valley. It represents the location for a minimum. Now, because this is the only critical value, we don't have a location that could represent a relative maximum, so this is going to be the only relative extreme value. So there at x equals 2, we have a relative minimum, and we don't have a relative maximum for this particular function. Well, what's going to be the actual relative minimum value? So again, we're going to take the critical value, that specific location, that specific x value, and plug it into the function. So f of 2 is 2 minus 2 raised to the 2/3 plus 1. And we don't actually need to do this in a calculator. We can do this probably by hand. 2 minus 2 is going to be 0. Well, 0 to any power is still just going to be 0. And then 0 plus 1 is going to be 1. So the relative minimum value is going to be 1, which means that's the lowest function value in relation to the values around it. So now let's go and let's graph the function and let's verify this, see what this looks like on this actual graph. So remember, this is the function representing the derivative, so let's clear that out. And then our actual function is x minus 2 raised to the 2/3 power. And then to that we are adding 1. So let's graph that. And I'm zoomed in, so let's zoom back to zoom standard. And there we go. This is what we see. So why was the derivative undefined at this location? Notice we have a point there at x equals 2. We can verify that on the table. There at x equals 2, notice the output was 1, which is what we expected based on the function evaluation we just did. But why did we have an issue with the derivative? Well, notice at that location we have what we could call a corner. We have a sharp point. It's not smooth as we transition from less to negative 2 to, or excuse me, less than 2 to 2 to greater than 2. So because we have that corner there, that is another situation where our derivative is undefined. So that's why we ended up with the issue we did in finding the critical values. So there aren't any locations on this graph where the slope of the tangent line would be 0, but at that one location the function is not differentiable, which again represents the possible location for a critical value, for a maximum, and something like this. But in relation to the other values around that, that's definitely the lowest value on the graph, so it represents a relative minimum. Okay, last but not least, let's talk a little bit about how we can generate graphs just using information about the derivative. So when you learn about graphing polynomial functions, graphing rational functions, you can plot points, you can find intercepts, you can find the locations for asymptotes, but in terms of getting a really accurate graph, you need calculus to be able to do that, to determine where your function is sloped upward, where it's sloped downward. Other than just plotting a bunch of points, that's hard to determine without understanding this idea of the derivative and what the derivative tells us. So having this idea of the first derivative test, where our function is increasing, where our function is decreasing, what the critical values represent in relation to other points around them, that's going to help us in drawing graphs. Now we're not going to focus too much on drawing really accurate graphs, but based on information we have about the derivative, we should be able to roughly sketch a graph that would meet those requirements. So our directions here are to sketch a graph of our function that would satisfy the following description. And one thing I want you to keep in mind is that there will be a variety of answers to a problem like this. There are a variety of graphs that would fit these requirements, but they just have to meet the requirements based on what we're specifying about the derivative. So what we know about the function here is that it has a positive derivative from negative infinity to negative 3, and it has a negative derivative from negative 3 to infinity. So more than likely, we can say that negative 3 is a critical value. Negative 3 is where we change from one behavior to the next. Now what does positive derivative mean? If the derivative is positive over this interval, that tells us that our graph is going to be increasing over that interval. And then if we have a negative derivative from negative 3 to infinity, that means our graph is decreasing over that interval. So here at negative 3, which I'm just going to put right here, at that location we transition from increasing to decreasing. So what could we say about negative 3 in that case? Well, that means negative 3 represents the location for a maximum. So we want to draw a graph that has a maximum point at negative 3, a relative maximum, and then is sloped downward to the left, and then sloped downward to the right if you look left, if you look right. Now what we don't know is what the actual point is at x equals negative 3. It could be up here, it could be down here. All we know is it's the highest point in relation to the points around it. So where you put the point, where we transition over, that's what's going to vary. I may put it one place, you may put it another place. As long as we're seeing the correct behavior with the derivatives in relation to increasing and decreasing, then we can both have two different graphs that are correct. So let's suppose the point is just somewhere right there. And again, that can vary. So for everything less than negative 3, we know we have a positive derivative, which means we're increasing from negative infinity to negative 3. So maybe we have something like this. Increasing from negative infinity to negative 3. And then from negative 3 to positive infinity, we're decreasing. So we have something maybe like that. So that's an example of a graph that would meet these requirements based on the values for the derivative. Now let's look at a slightly more complicated one. Okay, so same directions, new information about the function. So now we're sketching the graph of g of x, and we know that g of x has a negative derivative from negative infinity to 2, and then also from 5 to 9. So be careful, this is not an ordered pair, this is an interval. This is the interval from x equals 5 to x equals 9. And then we also have a positive derivative over the interval from 2 to 5, and then from 9 to infinity. So let's think about this. I'm going to draw a sign chart just to sort of sketch what we're thinking about before we put it on the graph. So where are the key locations where things change? Well, there at x equals 2, we transition from one behavior to another. At x equals 5, and then also at x equals 9. So those are going to be the key locations on this graph where things change. So x equals 2, x equals 5, and x equals 9. So we've been told that from negative infinity to 2, we have a negative derivative, which means we're decreasing. Our graph is sloped downward. Then from 2 to 5, we are increasing. We have a positive derivative, so the graph is increasing. From 5 to 9, we have a negative derivative again, so we're decreasing again. And then from 9 to infinity, we have a positive derivative, and we are increasing again. So these are the locations of our critical values. What can we say about the extreme points? What can we say about the points at each of these x values? Well, at 2, we go from decreasing to increasing, which means we have a relative minimum at that particular location. At 5, we go from increasing to decreasing, which means we have a maximum. And then at 9, again, we go from decreasing to increasing, which means we have a minimum. Okay, what is the minimum value at each of these locations? What is the maximum value? Again, we don't know. We don't know how far we dip down or how high up we peak. All we know is that those represent the locations and those points represent the locations where we transition from one behavior to another. So let's put those key locations on our x-axis. So we'll say this is 2, this is 5, this is 9, okay? Now as we go from negative infinity to 2, we're sloped downward. So let's pick a point. We want a minimum point, so let's put it down fairly low. Okay, so from negative infinity to 2, our graph is sloped downward. So maybe we have something like this, okay? Now once we hit 2, our graph begins to increase until we get to a maximum, a relative maximum, at x equals 5. Now it doesn't necessarily say that we jump above the x-axis. We could still have a maximum below, it doesn't matter. But let's suppose we have one above. So we have maybe a point right here. So from 2 to 5, we're increasing until we peak at x equals 5. So maybe we have something like that. Now from 5 to 9, we are sloped downward until we reach another minimum at 9. Now again, that doesn't mean we have to go as far down here. It doesn't mean we have to go even below the x-axis. It just means we have a valley in our graph. So maybe the valley is, maybe it's not as far down. Maybe it's something like that. So from 5 to 9, we're decreasing again. And so we have something like that. And then from 9 to infinity, we're increasing again. And so from that location, we're sloped upward, and it just continues indefinitely. So roughly speaking, we could have a graph like that. Now, in an ideal situation, we might have the locations of these maximum and minimum values in terms of the actual y value. So just knowing where the critical values are, all that tells us is really how we're shaped to the left and right of those locations. But knowing the actual y values, the function values associated with the maximum and minimum, that would help us to draw a slightly more accurate graph. but that gives you a general idea. So this idea of using the first derivative to find the locations for maximum and minimum values is going to be very, very important. Once we get to actual applied problems, we want to focus on maximum and minimum in the context of a real situation. Being able to find the derivative, use the derivative to interpret what we're seeing for a function is going to help us find locations where we can maximize a value and where we can minimize a value.